Okay, so you had a problem which was about, I think, a car, a toy car that was moving back and forth, and this was the rate of change graph. And you had to decide which one of these graphs showed the approximate rate of change function for the first 2 seconds using delta x of 0.5 and a left approach. Okay, so this was to see if you remember about us creating approximate rate of change functions from a exact rate of change function, and we wanted constant rates so that we could actually calculate change, right? With constant rate of change, it's easy to calculate change. So which one of these gave the approximate rate for the first 2 seconds using the left approach? Okay, so these two use a right approach. These two are getting constant rates from the right side, so it wouldn't be either of these. And so what's the difference between B and E? B takes us all the way to 2.5. So this, you can't really read this. This is 1. So part B would be 5 intervals taking us all the way to 2.5 seconds. And then E would be 4 intervals taking us to 2, and that's what we want. So E was the correct answer for this one. Okay? And so let's just recap what this was about. It was, so we have this function, f was our rate of change function. We call this f. Right? And what did we do this? We said if we had this approximate rate function, then we could make some kind of estimate of the total change in distance of the car, or displacement. Close those doors. I feel like I'm in an echo chamber. Thank you. So, and how did we do that? So we would take the constant rate, the first constant rate, which would be f of 0, times 0.5, and this would be our rate times change in x, and that will give us the little change for that first interval. And then we take the next rate, which would be f of 0.5 times 0.5. And then the third rate of change would be f of 1 times the change in time, 0.5. And finally, the fourth rate of change was f of 1.5 times 0.5. And what are we doing? We're summing up these approximate amounts of change in distance for each 0.5 seconds by doing m dx, right? M delta x plus m delta x. And we simplified that by saying we could use summation notation, right? We could say it's the sum, say as j goes from 1 to 4. And each one of them is a f, so f of, say, x sub j, right? So whatever that is, and then times 0.5. So we're just summing up a bunch of f of x is times 0.5, f of x times 0.5, f of x times 0.5. And so then when we sum them all up, we get the approximate amount of change in distance in the first 2 seconds. So that's all review. And then we said if we made, how could we get the exact change in distance? Yeah, so we make the intervals smaller, right? And then we say we make the intervals so super small that we can't tell the difference between the actual amount of change and then summing up all these proximal changes. So we make the intervals really super small. This summation notation becomes, should all be thinking integral, right? Integral, and it'd be from 0 to 2. And right there, so we see right there in the integral expression, we see what? M delta x. We're summing up a bunch of changes, in this case changes in distance, each one calculated by constant rate times the change in x, constant rate times the change in x. So this thing is exactly the same as this, except for super small intervals and a gazillion of them, right? Okay, so that's all review, and they're really important. Any questions on that whole process? All right, so if we look at this, say look at this one right here. F of 1 times 0.5. So if we go to that graph and we look, F of 1 is, how can we represent F of 1 in this graph, right? Wouldn't it be the height from the x-axis up to that point, right? Wouldn't that be F of 1? See that? And then the 0.5 would be what? This distance here. So this product, F of 1, or 0.5 times F of 1 would be this distance times this distance. And so we observe that that product could kind of represent something else besides a little amount of change. If we think of it as being this distance times this distance, then what else does that product represent? Do you see this area of a rectangle, right? Do you see that? Okay, and that kind of takes us to this picture here. So here's that, Here's that 0.5 that I just showed you, and here's that F of 1. And so when you multiply those together, you could, if you wanted to, you could view that as, could be viewed as area of a rectangle. But the reason this is true, it's just kind of coincidental to the fact that of the way that we graph, the way that we put x horizontally and y vertically at right angles to each other is the reason why it turns out to be an area of a rectangle. Okay? The area of the rectangle didn't come first. It happened to work out that way because of the way that we graph things. So seeing this as an area is kind of a coincidence, and it's not a very deep meaning. It's not a deep meaning. The way that we built it up in terms of rate of change and accumulation of the quantity. That's a deeper meaning. This is just kind of, oh look, it happens to turn out that also calculates the area of a rectangle. Unfortunately, in most calculus classes and textbooks, it's like this rectangle area is like the primary meaning, okay? But that's just incidental. That's coincidental. The real meaning behind this is rate. This is rate of change times the change of x gives you a little bit of change of the quantity. Okay, but there is some usefulness to this, and we'll see this in a second. But so we can now take a geometric perspective. And that still is important. So then all these four things summed together then would be the sum of all this area. So that ends up being 0 area, and then we get the area of this one. And then we get the area of this one. Okay, so this sum right here, we said is the approximate amount of change of our quantity, but it's also this amount of area, the sum of all these areas, where this is a 0 area here. So then the question is, as we make as those rectangles get smaller, what will our integral represent? So let's take a look at that. So any questions on what I just was talking about there? It's important. So we want our principal meaning to be that integral is about rate of change and the accumulation or the change in the amount of the quantity. But then we can take a geometric perspective, and that's where we're going now, where each one of these little products is now the area of a rectangle. Okay, can I erase? Any questions? So let's look at all right, there we go. That's what I wanted. I don't know why it didn't work. Okay, so this is what I showed you before. Okay, And so on that problem on the test, so what happens when you use more rectangles? Well, accurate to what? I mean, more accurate to what? Actual what? No, we're not taking. So we don't have a rate of. So we're asking in the new geometric perspective, what's going on, right? So yeah, so we get our approximate rate function gets closer to the actual rate function, but that would be for trying to calculate the total amount of accumulation or change in the quantity. Yeah. So now, if we're talking about those rectangles, and we use more and more rectangles, then what is becoming more? So now this is a whole bunch of rectangles. So summing up the areas of those rectangles is doing what?
Getting closer and closer to f of x dx. Calculating the area under that curve.
Yeah, so now the sum of those areas of those rectangles is getting closer and closer to what? The area between the curve and the x-axis. So let's see it again. So first we had that, and then more thinner rectangles, more thinner rectangles. Each time is that the total area of those rectangles is getting closer and closer to the total area between the curve and the x-axis. So here's super thin rectangles, which are what? The tops of those rectangles are matching the curve really, really well. And so now we're starting to talk about what the integral would represent, right? The integral would represent the sum of these areas of these sticks, basically. And so then that would be the area under the curve to the x-axis. So that blue, what I shaded in blue there, that area from 0 to the vertical line at 2, between the curve and the x-axis, that area could be represented now by the integral from 0 to 2 f of x dx. Before we said what? It was the total change in the quantity from 0 to 2, whose rate of change was f, right? Whose rate of change was f. But now f doesn't have to be a rate of change function. It could be any function. And we're interested in, for whatever reason, we're interested in the area under that red curve down to the x-axis. And so that's this new meaning for integral in terms of geometry. Does it make sense? I think now we're up to that. Okay. Question, please.
Yeah, so I guess going back to the exam, so are you saying that E is correct or both A and E are correct?
Okay, good question. So where is it? Oh, that was back at this. So what do you guys think?
E is correct.
E or both A and E?
Will you specify the left? Yeah, left.
But A is based on left, right? A is still left.
To use the rate of change.
Right, so what does it say? It says, which of the choices below shows the approximate rate of change function? So that's, light bulbs aren't going off.
They both show it, right?
No, what is this showing? This isn't showing a rate of change function. Yeah, Christiana.
Aren't you just saying that basically f dx is the area under the curve, which means that it's the quantity instead of the rate of change?
F dx. So hold on a second. So that's a different issue. So let's answer his question. He's saying is the answer A or is it A and E? Or sorry, E or A and E? So the question is asking for an approximate rate of change function. So does A show, is it depicting an approximate rate of change function? Yeah.
No, it's showing the area.
Yeah, so this is depicting a bunch of areas of rectangles. So yeah, you could say that the tops of those rectangles are the approximate rate function, but that's not what this graph is. If you have to only choose one, it would definitely be E, right? So E is showing the approximate rate function, where A is showing approximate area, right? It's showing these areas of rectangles. But if we want to, it's not really showing a function, it's showing a bunch of areas. This is showing a function of constant rates trying to be like the real rate. Did I answer it?
Yeah.
Yeah, so now, Christiana, is that the same? Okay. Okay. So if it said, which one of these was for area or geometric approach using the left side and delta x 0.5, then it would be A. Okay. So we're talking about now we're transitioning to integral as area. Okay. So we say this is not as deep a principle as the accumulation of a quantity, but still important for geometric purposes. Okay. So we can use our newfound knowledge here to say, do this. Find the area bounded by y equals 5x minus x squared on the x-axis. Okay, so the first thing is that we're going to have our graphing calculators, but there's some basic graphs that we should really be able to do by hand without our calculator. Yeah?
Isn't the principle of integral of accumulation of quantity in this kind of synonymous? Isn't once you find the exact area under a curve, isn't that the exact change in y of a?
Yeah, but so if you're talking about, say, distance and time doesn't have anything to do with area, so why talk about area? You see what I'm saying?
Yeah. Okay.
Yeah, that's the way it's framed in other calculus courses. It's find the area, and now that area represents this quantity. Well, why do that? You know what I mean? Why even have area in the first place? Because it's really, we have an approximate rate function. We're summing up amounts of the quantity, and then we get the actual amount of the quantity. Why inject area into it when it really has nothing to do with it? Does that make sense? But yes, you're right. That's how it's framed in the rest of the world. Okay? All right. So, we have our graphing calculator, but there's some basic sketches we should be able to do, like this one. All right, so could we make just a good enough sketch to solve this problem without our graphing calculator? So what kind of curve is this? 5x minus x squared? Okay, so we should recognize that as parabola, right? And then does it open up or down? Okay, it's a negative x squared that opens down. Okay, that's still a lot of parabolas. That's not enough for a good sketch, but that's a start. So one suggestion here is we could factor out x. And by factoring out x, what did we just help our? Okay, so x times 5 minus x tells us that. Okay, this gives us values of x that make y equal to 0, right? Values of x that make y equal to 0, so that gives us 0, 0, and 5, 0. And then we know that, so it's going to go through those 2 points, and we know that it opens down, and that's kind of all we need to make a sketch. Even though we don't know we haven't found out where the vertex is. That's okay. For this problem, we don't need to know that. There though. Okay, so now that we've got our sketch, we want the area bounded by y equals 5x minus x squared and the x-axis. Okay, so that clearly is this region right here. And so here's what we're going to do these. What we want to do is we want to consider what we call a typical strip. So we know a typical strip is like a really thin rectangle, okay? And so what do those rectangles look like? They look like this. So this is going to be called our typical strip, right? Because the whole region is made up of these. A lot of those, right? So the whole region is made up of a lot of these typical strips. And what we'll do is we'll calculate the area of one of those, and then we'll use the integral then to sum them all up. So what is the area of the typical strip? So we'll say And that's really a little bit of area. So that's like delta A. So what is the area of that? Well, base times height. So what is, that's the base of it. And this is the height of it. Here to here. So what is, so, and we're going to do base times height. What is the base width of that thing? Delta x, right? So just a little change in x. Okay, and when we, so this height, so that height could be one of four things. It could be just the x coordinate. It could be some change in x. It could be a y coordinate, or it could be some change in y. So which one of those four things is it? Is it x? Is it a change in x? Is it y or a change in y? So it's going from the x-axis up here to the curve. So it's simply just a value of y. Do you see that? It's the value of y for that curve. That's the height of this strip is the y coordinate of the curve. Why? Because the strip starts at the x-axis. All right. So since we have delta x, then we want to rewrite everything in terms of x. So y, what is the y coordinate of this in terms of x? Yeah. So the height of that strip is according to the curve. So it's going to be 5x minus x squared. Okay, and so now that we have our little area of a strip, what are we going to do? We're going to add up all those little areas. So summation, right? But then we're going to consider them as infinitely thin. So what kind of summation do we have? Integral, right? That's our summation. We're going to sum up all of the typical strips, which is base times height, base times height. And now we have the limits of integration are going to say which strips do we have? So where's the very first strip at x equals 0, and then we imagine all those strips lined up like that, and the very last one is at 5. And that's super easy, right? So that's our desired area. And you can all do that in your sleep, right? Get that value, whatever that value is. Okay, so could we have bypassed all this stuff? Yes. Please don't. When we get into the harder volumes and harder areas and the physics problems, this little thing right here, setting up in this case it'd be an area of a typical strip, before setting up the integral is going to really, really be helpful. So let's just practice it now on the easy ones. Okay? So yes, do this. Okay? Do this. Isolate one element. Isolate one element and find whatever quantity it is that you want about that one element. And then think about, all right, I'm going to sum all of them up, and that's your integral. Okay, questions on this? Okay, so let's do a variation on the same problem. And so now the integral from 0 to 8. So if we did from 0 to 8, same thing. Let's just do this in got my calculator here. So y equals 5x minus x squared. So I've squished or scaled out the y-axis considerably so we can actually see what's going on. So now we're going to do the same thing. Maybe. No. There we go. Okay, so we're going to do the same thing, but now from 0 to 8. So notice at 8, from 5 to 8, the function is negative, so what's the impact here? What's the impact on this? So if we were to do the integral from 0 to 8, 5x minus x squared, we want to go back to thinking about this as a rate of change and accumulation. So if this were our rate of change graph, and we did the integral from 0 to 8, what would that mean? Let's everyone involved here. Carl. So if that was that purple, if that curve was the rate of change, and I did the integral from 0 to 8, what would that be finding?
Area between the x-axis and
Okay, I'm framing it as rate of change and not geometry. So if I frame that as rate of change,
if it's just rate of change, you just have the total accumulation.
okay, the total accumulation. Okay, so can we be more? Where's Emily Nelson? Emily.
It would be meaning like you'd be going, the rate would be increasing at first, and then it'd be going like at a negative rate
Okay, where does it start at a negative rate?
at 5.
At 5, it's a negative rate. So then what does that mean for this? What's happening then if I did an integral from 0 to 8, what would that calculate? What was that?
A negative number.
A negative number, but what would it mean?
That the quantity has decreased.
What's that?
The quantity has decreased.
And why? So and why? Okay, so you're saying the quantity will have decreased because this will be a negative value. Okay. Any more to add? Where's Robert? Reese. Robert. So she's saying that will be a negative number because the quantity will have decreased between 0 and 8, from 0 to 8.
Would you have to set up those two integrals from 0 to 5?
Nope. I want to know what this means in terms of rate. What will this give? I want to know what this integral means. If this is a rate function, what will the integral from 0 to 8 give us? Not sure. Where is Zoe? Yeah. It'll give. It'll.
The accumulation of their rates as one cancels the other.
Okay. Okay. See what there's some volunteers. Yeah, Trevor.
Total change of accumulation.
Okay. So it's the total change. So if we accumulate at this rate, it'll be the total change in our quantity from 0 to 8. Right?
Well, we can't, without doing the math, necessarily say that it's negative.
Okay.
Because we don't know if going back to geometry to make things, explain things simpler, we don't know if the area after 5 is larger than the area before 5, as in we don't know if the negative accumulation is more than the positive.
Okay, so from 0 to 5, what happens to our quantity? Increases this whole way, right? Because we have positive rate. And then, starting at 5, the quantity decreases. That's what this calculates, right? Anytime the rate is negative, it'll bring that quantity, as the quantity accumulates, it'll bring that value down. Okay? Because what this is doing, this is truly doing what? F times dx, right? So whenever f is negative, the total accumulation of your quantity is going to be decreasing whenever f is negative. So what happens when we start thinking about areas? Yeah, exactly. So areas are always positive, but we're going to take f to be negative values between 5 and 8. So it's still going to have the effect of a reduction, right? A reduction. So if we think about the typical strips or the areas over here, it's really bad. Anyway, you get the idea. Yeah, so if you think about our typical strips over here, area is always positive. So the area of that strip is positive, but what the integral does is it will take the value of f as the height, and that value of f is negative. So that little strip will have a negative contribution to the integral. So just like with rate and accumulation, it'll increase, the accumulation will increase to 5 and then start decreasing after 5. The area also has the same effect. All this area will be adding up, but then when we hit 5, we'll start taking away from that area according to the opposite of those areas when f is negative. Does that make sense? Okay. So you guys were debating, is this going to be a negative or positive, right? Because all this area will get, call this A1, and this down here is A2. Those are both positive numbers. So in terms of A1 and A2, what will this integral calculate in terms of A1 and A2 as positive areas? What will this integral calculate? Where is Caitlin Murrock? Yeah. So in terms of A1 and A2, what will this integral calculate?
Just the difference.
So it would be what? Yeah.
So just A2 minus A1.
A2 minus A1. Which one's the positive one?
A1. So
Yeah, so this one's going to have the positive contribution, and this will have the negative contribution. Yeah, so it'll be the A1 minus A2. That's what that's going to calculate, that integral. All right, so place your bets. Who thinks this is going to be positive? Who thinks it's going to be negative? So right, so we had to just judge by the amount of area. Positive or negative? What do you think?
Perfectly zero.
Perfectly zero.
Just because you're screwing with us.
Oh, no, I don't even know. I don't have some exciting punchline for you. I just let's just estimate. So it'd be the integral from what, 0 to 8 of the negatives have it. So it ends up being negative 10 points, 10 and 2/3, negative 10 and 2/3. And why is the integral negative? Because this area down here, this area is bigger than this one, and it has a negative contribution to the integral. Okay, so what if I wanted to calculate A1 plus A2? So I don't want the difference. I want to actually know what the total area between the curve and the x-axis is. I can't use the integral from 0 to 8 because that's going to give me the difference of areas. So I want to know how am I going to get A1 plus A2? Yes, sir?
You need to take the absolute value of A2 or the entire function.
Okay. So you want to do tell me what you want to do.
So you would write it as the integral from 0 to 8
Uh-huh.
of the absolute value of 5x minus x squared dx.
What do you think? Will that do it? Yeah, because then anywhere the function is negative, it'll change it and make it positive. So we'd really be integrating what? We'd really be integrating a function that looks like this now. So this and then like this. So it would be that following there, and then it would flip up like this, and we get that area plus that area. Okay, but I don't really know how to do this integral, right? I don't know. I want to actually do this by hand and get the area. So how can I frame this so I can actually calculate something by hand? Because I don't know how to integrate the absolute value of 5x minus x squared. Somebody knew? Yeah.
You could do the integral from 0 to 5.
Right?
And then you could add the integral from 5 to 8. Subtract it. But you don't subtract it.
You want to?
Subtract it, right?
Yeah, so we could just add, we know that from 0 to 8, we're going to get the opposite of the area. So let's take the opposite of that. Sorry, 5 to 8. So if I isolate where the function is going to be negative, and then for those intervals take the opposite of the integral, then it'll give me the positive value of the area. And so now I'd actually be finding the total area of A1 plus A2. So let's do that. So from 0 to 5, we like it just as it is. But then from 5 to 8, we want the opposite of it. Certainly, so we know that's going to be positive, and it's a big positive value, now 52. Okay, so now that's giving me the total area of A1 plus A2, 52 and a third. Whereas the difference of the areas was the negative 10.7, the area below being greater. Okay, so really important concept. Doesn't make sense. Yeah, please.
Oh, wait, it was going back to, I had a question about the A1 minus A2.
Yeah.
So since it's the A1 is positive and then you're subtracting A2, which is negative, wouldn't that give you the total area instead of the net area?
Areas are always positive. When I write A on the board, that's a positive number. So when I say A2, I'm pointing at this and saying this is a positive value because area is always positive.
Okay.
Does that answer it? So now what does the integral calculate? It calculates this area minus this area. So A1 minus A2. So, yeah. So don't ever, whenever you represent an area like with a capital A, that's a positive value. Areas are always positive. But now we can subtract them. We can subtract those positive values to figure out what integrals are. Is there another question? Okay, so we said we're talking about integral as area, so now we've kind of refined that, and we want to be more general. Instead of integral is not really area, right? What is it? So what's a more general, rather than saying as area, to be more general and correct in all cases, we get what?
Accumulation of rate of change.
No, so we're still in geometric perspective. Still
Displacements.
yeah, difference of areas, right? Or net area. So integral isn't going to be an area necessarily, but it will always be a difference of areas. Okay, so that's what we can say. All right, so let's work on another one here. So can you sketch this region without a graphing calculator? You should be able to. So let's try that first. Can we sketch the area bounded by y equals 1/2 x cubed, x plus y equals 6, and the y-axis? Can you sketch that region without a graphing calculator? Give it a try. Okay, Hector, you're up. Any progress? Either of those? Can you tell me about either of those curves, sketches?
I was not touching.
Okay, so 1/2 x cubed. Where is, how about George? Where's George? George Strong? There's not here.
So x cubed goes through the origin.
Okay. Adrian, saving us.
X cubed goes through the origin.
Yeah.
Yeah.
Yeah, but I already done the S when I got to the origin, right? So the origin, then it's concave up from there. So that's y equals x cubed. We're doing 1/2. Hopefully we got that. Okay, what about x plus y equals 6? Levi, did you get that? X plus y equals 6? Sketch of that? Yeah, so you could rewrite it if you want to. Y equals 6 minus x, and we all should be able to sketch that, no problem. Why? Yeah.
It's just y intercept is 6.
Yep.
Decreasing in line. Just the line
Right. Decreasing at what rate?
1
1 to 1, right? Negative 1. So where's across the x-axis? Also it's 6. Okay, so we have to read really carefully here, because now two regions are kind of emerging here. So we want that on the y-axis. So which region is it? Yeah, the one that's touching the y-axis. What's another way to write the y-axis mathematically? X equals 0. Make sure you know that x equals 0 is the y-axis and not the x-axis. This is a very common mistake students are not confident about. X equals 0 is all points where x is 0. I mean, we don't go to the right or the left. That gives us the whole y-axis, right? All points on the y-axis have an x coordinate of 0. Likewise, the x-axis is? All points on the x-axis have y equal to 0. So make sure you don't fumble that, because if you fumble that, then you have the wrong region, okay? All right, so here we are. And again, we're going to set up our typical strip. I beg of you, do this. Don't go straight to the integral. This is going to pay big dividends when we get harder things that we're integrating. Okay? Maybe easy with areas. Okay, so we're going to have a typical strip.
Professor,
Yeah.
don't you have to find the where 1/2 x cubed?
Yeah, eventually we will. Let's do our typical strip and we'll cross that bridge when we come to it. But yes, you're correct. So we're going to do the area of a strip. So a little change in area. Okay, and that's going to be base times height. What is the base? Delta x. Okay, the height. Is it an x coordinate, a y coordinate, a change in x, or a change in y? Do you see that that height is a change in y? It's the change from this lower, say call this y1 to y2. So if the bottom is at height y1 and the top is at y2, how can we express that change in height? Or change in y? y2 minus y1. But now since we're doing delta x, we want to rewrite that whole thing in terms of x. So we're going to rewrite y2 in terms of x. What is y2 in terms of x? That's our 6 minus x. And what is our y1? That's our curve. That's our 1/2 x cubed. Delta x. Okay, so we got our typical strip. And now the question is, and we're ready to sum those all up. Starting at x equals, y(x) equals. So we're going to get all these typical strips with a height of 6 minus x minus 1/2 x cubed with a width of dx. And then the first one is here at x equals 0. And the last one is at the intersection, right? So what is the x coordinate right there? Yeah, where the what are equal. where the y values are equal, right? So we want the x where those y values are equal. And so can we kind of see where that's going to be, just without doing a bunch of math here?
6 minus x equals 1.
Yeah, so that would be the math way, which is not very friendly at this point. That's not a very friendly thing to solve, except if you had a graph. So can we kind of...
You can assume it's going to be a whole number.
Yeah, if it's a... Yeah, so if we were to assume it's a whole number, what would that x be?
2.
Try 2. So 6 minus 2 is 4. 1/2, 2 cubed is 4. Check. Because all real-world problems work out really nicely, right? No, they don't. But this one is rigged, okay? So that's it. Another super easy one to solve. And what is that going to calculate? We're summing up, right? Summing up all these typical strips, which sum up to give us that whole area there. And it's time to go. So just thinking about, as you pack up, don't talk. Just think about this. What if it was on the x-axis? So those same two curves and the x-axis. Then we'd have what? This right here. And let's think about our typical strip. There's something different about this. We pick a typical strip, but we see that typical strip, what happens to the typical strip as we go all the way from left to right? Right here, the height of that typical strip changes. For the first part of the region, the typical strip has a height of the 1/2 x cubed, and then past that intersection point, now the 6 minus x is the top. So to get that area, we need to separate it into two different. There's not one integral that can give us the typical strip for the whole way across. So we need two different integrals.
Could you translate?
We'll do yes
Alright.
to y. Yeah. All right. So go to recitation if you have it. We'll have test results on Wednesday.